Okay, here's a little bit more on the topic of splitters. I've talked about excess loss, I've talked about the basic specifications. I want to talk a little bit more about the mode confinement, and I also want to talk a little bit more about the 2x2, the 1x2 Y branch in particular. And some of the behavior of that Y branch based on the propagation of the mode through the waveguide. First thing I want to do is I want to talk about, probably for the third video where I mention this, but here I'll try to do it a little bit more completely, is to talk about mode confinement. Okay. If we have a mode that looks like this, this is the lowest order mode in our waveguide, versus a mode that looks like this. Okay, these are both the lowest order mode, but they have very different confinement. This one has less or poorly confined field or mode, and this is a well confined mode. It turns out that in integrated optic devices, well confined modes have less loss. And that's because the imperfections in the waveguide, so let me draw this as N2 and 1, and this is my waveguide profile. If you have imperfections in the edge of the waveguide, and these inevitably result from fabrication processes, those imperfections will cause poorly confined modes to be very high loss. Okay, and so we want a well-confined mode. So we want well-confined M equals 0 mode, and we also want no M equals 1 mode. If we have an M equals 1 mode, then some of our light will inevitably escape from the M equals 0 mode into the M equals 1 mode, and it won't be able to be coupled back into the fiber. What we're going to see is that the fiber mode couples into the M equals 0 mode. Because we're dealing with single mode fiber. Almost universally in these types of integrated optic devices where we're pigtailing a substrate where you've got single mode fiber. Here. And that single mode fiber then has an M equals 0 mode, and its mode shape is more or less matching the mode shape inside the integrated optic device. And so we want to have a well-confined M equals 0 mode, and we don't want to have an M equals 1 mode. And so what I'll do is I'll draw my mode diagram again. I'm showing this for the second time. N2 up to N1, and this is D by lambda, and I'll draw I'm not going to label these, but these are the cutoffs for the different modes. Here's my mode diagram. Here's the cutoff for mode number 2. So if we have a waveguide where D by lambda is down here in case number 1 versus case number 2 versus case number 3. And in case number 1 we have an effective index which is very close to N2, which is the cladding. which means that we have a poorly confined mode. Okay? Because a lot of the energy is out in the cladding, meaning the effective index is closer to the cladding index. Here we have a much higher ineffective, meaning we have a more well-confined mode. In 3, we have 2 modes. Which is really bad, because when we couple from the input fiber into the waveguide, what's going to happen is most of the energy is going to go into the m equals 0 mode in the waveguide, but then some of it's going to leak out into the m equals 1 mode, and that m equals 1 mode cannot be coupled back into the fiber on the output. Okay, and so this is the basic idea of the mode confinement. Another point I'd like to make in this video, which is new, this point was made in an earlier video very quickly though, is that the 1/2 Y branch is symmetric in its behavior. The loss in either direction is 3 dB. And so if we have a Y branch here, and we bring light in here, and we have nothing going in here, then P out is going to be 3 dB lower. And that's due to the fact that the mode in this waveguide is different from the mode in the region where we've got a very different profile to our waveguide. In this region here where we have the Y branch, we have a very complicated mode structure, and it turns out that this mode can couple into the mode in the output waveguide, but half of the energy is lost. And that's a symmetrical situation. If we put in power into the single side, it's going to split off into 3 dB down into each of the 2 sides. So this is a sort of an interesting fact about a 1/2 Y branch. The other thing I'd like to do in this video is give you a very quick overview of multiple splitters. Okay. These are used very often in passive optical networks, which we'll explain. But we can have a 1/2, we can have a 1/4, a 1/8, 1/16, 1/32. I think 32 is about as high as we normally go. The intrinsic loss is 3 dB per split. So the output is 3 dB down when you have a 1/2. It's 6 dB down when you have a 1/4, 9 dB, 12 dB, and 15 dB. Those are the intrinsic loss values. Excess loss adds to all of that. And so, for example, in a 1/4 is just a cascaded 1/2. Something like this. Okay, so we've got 3 dB loss at each Y branch. Okay, let's see. And these things can be made and sold, and they're very useful. Oftentimes we will use ribbon connectors at the output. Okay, I think I'll leave it there for this video. Thank you.